So welcome to the David Sprott Distinguished Speaker Series. I'm Stefan Snyder. I'm going to be chairing the session here. So before I get to introducing our speaker, just a bit of background for those of you who perhaps aren't familiar with David Sprott. So David Sprott in 1967 was the founding dean of the faculty as well as the founding chair of the Department of Statistics, as it was called at that time. And of course we owe him a great debt of gratitude for the early growth and success of the department. The goal of the seminar series is to invite distinguished statistical scientists to come to Waterloo for a day or two to meet faculty, talk to students, and of course to give a seminar as we do today. Finally, the other thing I wanted to mention is before we go to the introduction is that we have a reception right after this talk, and that'll be taking place in the M3 building in the atrium. So please join us for the reception as well. So introduction of the speaker for today. We have Susan Murphy visiting us. So Susan received her PhD in statistics from the University of North Carolina, and just recently, like 5 weeks ago, I believe, moved to Harvard University. Before that, she spent around 19 years, I believe, at the University of Michigan. Susan's primary research interests include the development of experimental designs and statistical machine learning methods for informing sequential decision-making in mobile health. She's going to talk to us a little bit about today. Susan has been awarded many things over her career, including being a fellow of the Institute of Mathematical Statistics, a fellow of the College on Problems in Drug Dependence. She's also a former editor of the Annals of Statistics, and she's also a member of the U.S. National Academy of Sciences and the U.S. National Academy of Medicine, and is also a 2013 MacArthur Fellow. And on a more personal note, those of us who were at lunch discovered something very surprising, at least for me, surprising about Susan. Despite growing up in southern Louisiana, Susan is a very avid hockey fan, and she told us she would never have moved to Harvard except for the fact that they had a league that she could play hockey in there in Boston. So I'll turn it over now to Susan.
Thanks so much for the nice invitation. And that is indeed true. I wouldn't even interview at a place that didn't have ice hockey. I mean, you've got to keep your principles straight, right? I mean, what more can you want in life? I want to be upfront with everybody. I changed the type of the talk. I won't be talking about online learning. We have a trial that is going into the field in December, January, and we will be using an online RL algorithm, but we're having a lot of problems in preparing for it, and I just didn't feel like we were ready to share that just yet. I could only give you challenges and no solutions. So what I'm going to do today is I'm going to talk about the study that we conducted in preparation to lead us to this study, in which we will use an online algorithm. And this actually helps us essentially construct a warm start. Now, I'm not going to explicitly talk about the construction of the warm start until the end, but that is what's going on here. It's part of what's going on here. I just wanted to mention this. It was a great honor it was very enjoyable to read about David Sprott. I mean, this guy was really interesting. He was around in the foundations of the statistical field. He was part of this whole controversy between what we call significance testing and hypothesis testing. Nowadays, we really call it hypothesis testing, but at the time, there was a distinction. And I'm going to be following his and Fisher's approach of significance testing in the sense that I just look to reject a hypothesis. That's how I collect evidence, is by rejecting hypotheses. However, Dr. Sprott was also someone who really believes strongly in likelihood inference. I will not be doing likelihood inference here, so I'll both align myself with his approach and disalign myself at the same time. I'll follow both. So as Stefan mentioned, my interest is in mobile health. And our lab, I run a lab in which we're involved in a whole variety of mobile health intervention development in physical activity, smoking cessation, in substance abuse as well. Today we're going to focus on the physical activity study. This is a series of 3 studies, and I'll report to you on the first of the 3. First I want to provide an introduction to mobile health. One of the things is when I go through this introduction, often when I speak with my CS colleagues, they wonder why I spend so much time outlining the parts of a mobile health intervention. And part of that is because statistics can have something to say at each of these parts, and by identifying the components, we're better able to figure out how to improve each aspect. So heart steps, this is, as I said, it's the first of 3 studies. This first study is with sedentary individuals. The next 2 will be with people who had heart attacks. And the idea is to help people be more active and maintain that activity. This is in this particular study, it's very short. It's only 42 days. The next one will be 90, and the last will be a year. Here the participants all wore a wearable band, a tracker, jawbone. It tracks their step count and some low-level measure of sleep quality. Of course, there's a lot of sensors on the phone. We know a person's location, the current weather, time of day, of course. We also have the ability to look at how busy their calendar is over the next couple hours. And then every evening there's some self-report. And one of the questions that you might ask, and this is all about learning how to tailor the intervention to the user, is in what context, the context is provided by this data, should the smartphone ping the user, interrupt the user, and provide a tailored activity suggestion? So these kinds of problems can't be taken willy-nilly. You have to be serious about this because every time you interrupt a user, you increase the burden you're placing on them. So their burden goes up every time you interrupt them, and also they begin to habituate to the messages. By that I mean they eventually don't even see the message. So there's a real trade-off between providing help, helping them, and burdening them and having them disengage. You have to think about when should you provide this. So how does the data, in this particular study, we're going to have time series of data on each individual in the study. And here I've listed a time series. So you have a vector of observations, includes baseline data, A for what I'll call an action or a treatment. I'll give you an example of this shortly. Then Y is some sort of proximal near-time response. Depending on the field, it carries a variety of names. So you have observation, action, response, and so on and so forth. These occur at decision points, and we'll talk about that next. So what are decision points in the context of mobile health? These are times at which you might provide an action, at which you might interrupt the individual. And usually you think of these as occurring regular intervals in time, say every minute. In the case of heart steps, we originally were going to consider interrupting or providing support at any minute of the day, but looking at a large amount of tracker data for people who are sedentary and have regular jobs, we discovered that there was a lot of within-person variance in their physical activity around 5 times a day. So high within-person variance indicates there's the potential to increase their activity during those times. And these 5 times are given below. They're approximately every 2 to 2.5 hours, pre-morning commute, and so on. So the decision points here are these 5 times every day on each individual. It's a 42-day study. We're involved in a smoking cessation study in which the decision times are every single minute. So every single minute we have the opportunity to provide a notification. So it just depends on the setting, the choice of these decision times. Observations, so they come in 2 flavors. You have the sensed data, the data we sense either via sensors that are being worn or on the phone. And then you have the actively collected data. And as you can well imagine in this field, a big push by many engineers, by many computer scientists, statisticians, is to reduce the amount of actively collected data. Because every time you actively ask for self-report, you increase the burden on the individual. And I list some of the data we collect in Heart Steps. There is a classifier on the phone, and it classifies whether or not one is moving so fast they might be driving a vehicle versus walking versus being sedentary or relatively sedentary. So treatments, we call them actions. There's types of treatments we could provide. So it turns out in this field, at first, when I first got into it, I thought there wasn't much you could do with a mobile phone. But it turns out there's an enormous variety of interventions or treatments that can be provided at a decision at any given time. So for example, if you're talking about smoking cessation and someone has a lapse, a treatment could be a cognitive message to help them reframe that lapse so that they can try and continue to stop smoking. You can have social support treatments where someone is feeling a lot of stress, and there can be an automated text message to a mentor to contact that person to help them out. There can be activity suggestions. We're going to talk about that shortly. There's motivational kinds of messages that you can provide to help someone continue to stay on target so that they can try and achieve their goals. And of course, the other type of treatment decision we can make, types of treatments, whether to provide a treatment at all. And this goes back to the statements I made at the very beginning, earlier on. Every time you intervene, every time you provide a notification, associated with that notification is the potential for burden and the increase in habituation. So often, and today, we're going to focus, at least at the beginning of this talk, we're going to focus on whether to provide a treatment at all. And it's because of these iatrogenic effects that notifying someone, interrupting them, can have. That there's between nothing and something. And I just want to give you an example of what those, in the case of Heart Steps, what a notification would look like. This comes up on the top of your phone, and it's a tailored message. So it's tailored to the weather outside, whether you're at home or at work, the time of day. And this one came up, it was cold that day, but it says, hey, look, it was in the morning. Hey, look, outside, it's not so bad. Maybe you could walk to work or just park a bit further away. So it's intended to be actionable in the near time, approximately in time. Always tailored, though. When I get this, it would come up on the top. It's a notification. It comes on the front of my screen. I have 3 ways to wipe off this notification. I can press thumbs down. I didn't think it was so useful, so it goes away. I can press thumbs up. I like the message. It goes away. Or I could press this middle button. If I press this middle button, a drop-down menu comes on, and I get the option to turn off the intervention for 4, 8, or 12 hours. So it's really great. I'm going into a big meeting that's going to go on for half a day. I just turn off the intervention. It's not going to ping me. My phone won't light up. I won't get any audible messages. So the user has the control here to turn off the provision of these messages. I just want to make one more point. Mary and I had this discussion earlier. This is an example of something to help me be physically active in that moment. But we can also have another type of treatment called an engagement strategy. And we're actually working, afterwards, if people want to talk to me about it, we have a study in the field right now where all the actions are engagement strategies. And this is to deal with a really big problem we have nowadays in mobile health. If you've ever downloaded an app, you know exactly what I mean. People, maybe they'll use it 1 or 2 times. They usually delete the app pretty fast. So how do we keep you engaged enough so that we're there to provide support when you need it? That's what the engagement strategies are about. Okay, so this is there's something that comes up in this setting. I tried to avoid it. It comes up routinely in sequential decision making, for example, in robotics. But here it plays a more prominent role. And so we have a special terminology for it. So we can only provide a treatment at a decision point if the person is currently available. So there are some contexts in which the person is not available. You don't even think about providing a treatment, a notification. In the case of heart steps, if the activity classifier on the phone states that you're going so fast you might be operating a vehicle, you're considered not available. We will not ping, notify you, and potentially interrupt your driving, for example, distract you from your driving. Because all our messages are messages about taking on a new activity, like going for a new walk, if you're currently walking, we consider you unavailable. Because if you're already walking, we don't want to suggest a different walk. Now, if our messages were all about extending the current walk, it would be different. But that's not the case here. So you're unavailable if you're currently walking. You're unavailable if you might be operating a vehicle. And the only other time you're unavailable in this particular, in heart steps, is if you turned off the intervention, because you have the right to turn it off. So when I ask, is there an effect of our activity suggestion versus no activity suggestion, I'm going to ask it always conditional on availability. Among the people who are available at this time, is it worth it to provide an activity suggestion versus not provide an activity suggestion? At every time, you're talking about a different subpopulation of individuals, right? In fact, I'm just going to say, think about who is likely not to be available due to currently walking. If I've really drank this Kool-Aid, right? I really love this intervention. I'm walking every time I get an activity suggestion. I might start walking at those 5 times a day or be more likely to walk. And so thus I'm less available. So the effect is always among those people who are available at that time. The last statement here is for the statisticians. Many people tend to think availability, it's very easy to think availability is the same as adherence. But availability is ascertained before we even decide whether or not to provide an intervention. Adherence is me, the user, saying, oh, you pinged me, I have no interest in looking at that message, I'm just going to leave it in my backpack and walk away. That's non-adherence. That's completely different from availability or non-availability. And what's our outcome in the case of heart steps? Well, these little messages, as I mentioned earlier, they're intended to help one be more active in the moment. So our proximal outcome is the step count in the 30 minutes following the decision point. Again, 42-day study, 5 decision points per day. At each decision point, you may or may not get a suggestion, a tailored activity suggestion, and what is your subsequent step count subsequent to that time point? Now, it would be great, and in fact, we would love for you to remember these suggestions and use them at later times. So we're not trying to, we want delayed effects, it's fine. But our focus is on, do these suggestions have an impact on your step count? 30-minute step count. So in most of the mobile health interventions I'm involved with, there is a proximal outcome, some near-term outcome that we are trying to impact by delivering these notifications. I just wanted to give you an overview of what our lab does before we continue on with this. So we've worked on trial designs. How do you assess if there's effects on the proximal outcome or response? Today we're going to talk about causal inference in this setting. Do the effects vary by internal, external context? And as I mentioned earlier, we're working on algorithms for using the information that we gain from trials to warm start our reinforcement learning algorithms and then run them online. And I can talk to people about that. It's quite interesting in mobile health. Standard reinforcement learning algorithms really need a lot of work. They're not, you can't take them off the shelf. Okay, so I just want to tell you about the way this trial was run in HeartSteps. This was what we talk about as we call it a micro-randomized trial. So in a micro-randomized trial, on each of the participants and in each of the decision points, we have 42 days, 5 decision points per day, so 210 decision points per participant. You have this information. You have the observations, like we talked about. You have whether or not they were available at that decision point. You have whether or not they're treated or not, whether they get an activity message. These activity messages are going to be randomized, and we know the probability of randomization. It's some function that depends on the past history of the individual, all the data we collected up to that time. And then we have some proximal outcome or response. In the case of HeartSteps, was the 30-minute step count. Here, I just want to make a statement about HeartSteps. The randomization probabilities in HeartSteps are very simple. We wanted to provide an average of around 3 messages per day, and we had 5 decision times, so the randomization was 3/5, 0.6. But in we have 2 other studies right now where the actual randomization algorithm we're using is itself an online algorithm, which is continually updating the probabilities so as to spread out the interventions across the day. The key here in this entire talk is that I know this formula. I know what it is. I can reconstruct what that probability is. Okay, so now I have the data. I ran the micro-randomized study where I just randomized with probability 0.6. I provide a notification at a decision time. With probability 0.4, we don't bother you. 42 days, 5 times a day this happens. And so how are we going to analyze that data? So I had made up these slides. I talked about this study to a group of cognitive neuroscientists. And so I wanted to make the slides very conceptual and not very technical. And then I realized they help me understand the problem too better. So I'm just going to go through that with you, and then I'll bring in more of the technical part. So let's think about how people analyze data where you have randomization. The first analysis is usually you just have an indicator of randomization. 1, if I provide a suggestion, 0, not. A is 1. You get a suggestion, 0, not. And then you also have some other variables you put in your model. And then you have your outcome here. That's usually the first analysis you run. And then after that, you run a sequence of secondary analyses where you put in variables that describe the context. Here I said current weather is good or not. And these can be really sophisticated depending on the amount of data you have. There can be basis functions in here and so on. But in general, the way we first start off, we have a simple model is with an indicator of treatment, and then we have more complex models. And this is generally the way behavioral scientists would analyze mobile health data, or they might think about analyzing mobile health data. And these parts of the model, they play conceptually distinct roles. And it's important to understand those conceptually distinct roles when we go to try and use these ideas to provide a method for mobile health. So first, I'm going to talk about the role that part in blue plays. So the purpose of these variables, the variables that are in particular here Z, is this is a vector of covariates, and the whole purpose is to increase the signal-to-noise ratio. That's the whole purpose, reduce variance, increase signal-to-noise. In fact, they're often called control variables because you're trying to control the noise level. If you worked in clinical trials, there's a very popular control variable which is almost always used. If you have a pre-treatment measure of the outcome, you almost always control for it. So in our case, in HeartSteps, we're going to control for the prior 30-minute step count, right? Because that's prior to the randomization at any decision time, and the outcome is the post 30-minute step count. So you always try to use the pre-treatment measure of the outcome. Usually, and it's great, it works great because you really reduce the noise in these problems. You have a much better chance of seeing a signal. So we're going to want to do that here when we develop a method. We're going to want to allow people to do that. And then all the science comes up in the second part of this conceptual model, this part of the model that has the beta weights. So let me discuss the interpretation of this first coefficient. That, remember, A is 1 if you get a message, 0 if you don't. So what does beta 0 mean here? How does it get interpreted from a conceptual point of view? It's understood to be marginal. It's an average effect of, what is the effect on your step count, your subsequent step count, if you get an activity message versus if you don't. On average, does it increase your activity over the next 30 minutes versus not? It's marginal because it's marginal over your gender. It's marginal over the time of day. It's marginal over whether you're at home or at work, whether the weather's bad or good. But it's causal. We randomized whether or not we'd provide a suggestion. So it's a causal quantity, but it is marginal over all kinds of things. And we understand that. We understand both of those aspects of the interpretation of beta 0. Then we start adding variables from the context. Here, ST is 1 if the weather's good, 0 otherwise. And so now, when weather is good, the effect of giving a message versus not giving a message is the sum of these two coefficients. Now we got a little bit more person-specific in the sense that the current weather is being taken into account, but it's still marginal. It's marginal over gender. It's marginal over the day of the week, the time of the day, and so on. It's marginal over how busy my calendar looks. So no matter what, this effect that we always get, it's always marginal over a whole host of things. The variables that either we don't have observations for, so we can't include them, or that we choose not to include. It is causal. It's always causal. It is giving us estimating this sum does give us an estimate of the effect on your subsequent activity of getting a message versus not getting a message. Causal, but marginal. So what's our goal? Our goal is to develop data analytic methods that are consistent with the understanding of this causal marginal understanding, the understanding that's used throughout the behavioral sciences for these effects. But there's some really big challenges, and if you're familiar with causal inference, you're ahead of me. First of all, our treatment, whether or not we give you a suggestion each of those 210 times, it's time varying. And the variables that I'm controlling for they should be independent. They shouldn't be impacted by treatment, but they're clearly impacted by treatment. So let's go through that. Whether or not I'm available at a particular time could be impacted by past treatment. Z, which might include my pre-decision time. Suppose we're in the morning and we're at a decision time. Z will include my activity prior to that decision time. That could have been impacted by treatment on the prior day. So our variables that one might call independent variables, they're affected by prior treatment. So this has the potential to cause a lot of problems if you're doing causal inference. And why are we doing, let's just be clear about this, why am I so fixated on causal inference? Because I really want to know what's the impact of providing a message versus not. I don't want to provide messages if there's not a good impact, because there's so much heterogeneous nature. I mean, if I interrupt people too much, they disengage. Also, another goal we want to do is we want to allow scientists to increase the signal-to-noise ratio. We want to facilitate noise reduction. And in standard clinical trials, one can do this, and you don't have to worry. It's a one-time randomization. You don't have to worry about how you parameterize that, as long as you want to pre-specify it. We're going to want to achieve these goals. So the way I have to be really clear, first of all, about what it is I'm estimating. In English, I told you about this causal marginal effect. And the way I'm going to be clear about it is I'm going to use the language of causal inference. That is, I'm going to use the language of potential outcomes to precisely state what I'm estimating. I call these causal excursions. I'll explain why shortly. It's quite interesting. I got this word excursion from Rich Sutton has these ideas of excursions in AI, in robotics, and it has the exact same meaning in this context as well. Okay, so potential outcomes. So the idea of potential outcomes is you take each variable, each outcome, and you index it by all the treatments that you can manipulate, that you would like to be able to manipulate. So let's think, so first of all, here's the treatments that we're manipulating, whether to send a message or not. They're at time t, so these are all randomized treatments. We get one realization. This is a pattern of ones and zeros. There's 2 to the t possible patterns of ones and zeros, realizations of treatments. We think of a potential response to that pattern of ones and zeros. This is my step count in the subsequent 30 minutes. It could be impacted by that pattern. So if that pattern is all ones, I got a message at every single time, that may have an impact on my step count subsequent to that. Then we have availability. Availability now is a little different. It's not like the proximal response. Availability can only be impacted by my past treatment, not my current treatment. That's the reason why there's a t-1 here instead of a t. So current treatment is AT. Past treatment is all the treatment up to time t-1. Remember, availability is prior to treatment. And then, of course, the history vector is also can be impacted by how I was treated in the past. So what are we estimating here when we talked about those causal effects? So here I'm going to write it in terms of these potential outcomes. There's no data involved right now. It's just potential outcomes. So I know this is causal because this is a contrast between getting a message at time t, that's 1, versus not getting a message at time t, that's 0. So this is a contrast between my step count at following time t, getting a message versus not. So it's a causal contrast. That's standard causal inference, nothing special here. It's marginal over any variables that I didn't include in my context at the time. It's, for example, if ST doesn't include gender, it's marginal over gender. It's marginal over current weather, my current location, if that's not in here. But it's conditional on availability. I have to be available or we're not even interested. If you're currently driving, I am not interested in the impact of sending an activity suggestion to you versus not. So it's marginal over the variables that I don't include in this conditioning statement. But it's still a contrast between getting a message versus not. It's kind of, the thing that's unusual about this, that's very unusual in the causal inference literature, is the fact that this expectation, which is averaging over distributions, it's averaging over the step count that you would expect to see subsequent to a decision point. It's also averaging over how I came to be treated prior to that time. This is very different in causal inference. Normally, in causal inference, we strive to make our estimates not depend on how we're treating. This is the reason why I call this an excursion. So think about it. A person is going along. They're experiencing the intervention as it's being provided to them, whatever randomization algorithm I'm using. They're experiencing it. I get to time t. And I think, well, let's say for sure I get a treatment. I take an excursion in which for sure I get a treatment at the next instant versus an excursion in which for sure I don't get a treatment at the next instant. What is my behavior after that? So that's why we call it a causal excursion. And in fact, in other settings, we go out further. So we say, we're at the beginning of a day. We've been treated in a certain way up to that time. What will my behavior be over this day if I don't get treatment at the next 5 times versus I get treatment at the next 5 times. So excursions can last for a duration of time. They can just be for 1 unit at a time, or they can go over a period of time. In this case, we're just going over 1 unit at a time. So our excursion is get a treatment next, or don't get a treatment next. So how do I connect that to the real data? The kind of data I'm going to get, the real data isn't indexed by A's. It's just a YT plus 1. So if you're familiar with causal inference, there's 2 ways that always they come up repeatedly all the time in causal inference. The first way is you express your causal estimand as a series of repeated conditional expectations. And that's the way I expressed it here. I have the inside expectation is conditional on the entire history of the individual up to that time. Got treated, didn't get treated. Always conditional on the entire history. The external expectation is only on the part of the context that I'm interested in looking at it in this analysis. So that's classic. I mean, if you're familiar with Robin's work, this comes up all the time. The other way in which you can express a causal estimate in terms of the distribution of the data is by using the randomization probabilities by importance weighting or propensity scores, depending on your field. So here, these are all equivalent. As long as I have randomization, essentially, if you have randomization, they're all equivalent to this expression in terms of potential outcomes. So here I'm using weights. I weight by the probability you got a treatment, and the numerator has the indicator of 1 if you get a treatment. Here, the indicator is 1 if you don't get a treatment, and I weight by the probability of not getting a treatment. These are the 2 ways that you always see causal inference estimands. And that happens here because we're doing our randomization. So what we're going to do here, I'm going to talk to you about a method for all we're going to do is model the treatment effect. So what I'm going to give, I'm comparing getting a message at a decision time versus not getting a message on your subsequent step count among the people who are available, and maybe whether or not how active they've been over the last couple of days. I might include that in the context. I'm going to model it. I'm going to use a very simple linear model for this discussion. Our goal is to conduct inference about beta. Okay. This is all we're going to model. We're not going to model anything else. And if you've ever seen step count data, I don't know, have any of you ever seen step count data? It almost looks very chaotic. It's highly complex data. We're not going to model anything else but this treatment effect. This is going to really save us by focusing on the treatment effect only. So I'm going to give you in the next slides, I'm going to give you an estimation method. The very first time I talked about this estimation method, the first time we developed it, it was really complex, and we submitted it to a journal. And the reviewers came back, and they had tons of questions. And then when we thought about it, we realized, we didn't need to make this method very complex. In fact, it's extremely simple. And if you're a standard classical statistician like me, at first you're kind of disappointed because you want things to be complex because then they're cool. But in fact, it's better in the end. And it has been better for us because this is a simple method. So we're going to see it in the next slides. So we call it centered and weighted least squares. It's a simple method for very complex data, such as step count data. What it's going to do is it's going to allow us to obtain unbiased inference for these marginal causal effects. And even more importantly, it's going to allow us to increase the signal-to-noise ratio by appropriately managing how we use controls. This is going to be a real boon here. And the reason why it's a boon is because let's say T, capital T, was time 200. The amount of data we have on that individual at time 200 is vast. It would be nice not to have to get a model correct, yet still increase the signal-to-noise ratio. So that's the game here. So I'm just going to tell you the method, and then we'll go through about it. So first of all, you select some probabilities, and you then form, I'll tell you about how to select it shortly. So these are probabilities that you select. Think of it, they're not quite tuning parameters. We're going to talk about how you would select them. Then you form what people would call importance weights or ratios. So this is my randomization probability here, the probability of getting a message, the probability of not getting a message, that's in the denominator. You center your treatment actions. They were binary 1 and 0. Now they're going to have mean 0. They're centered. They have mean 0 under the numerator. And then you fit what appears to be a simple linear regression. Or this could be complex features, but it appears to be a simple weighted linear regression. See my weights here? They're there. The indicator of availability is there. And it just looks like, and then you have this EN means just average it over all the individuals in your study. I mean, it's just very low level. Okay. So I've just given you this, I'm going to minimize this least squares, this weighted least squares. It's very simple. So if you're like me, there's several things that I would jump to when I see a weighted least squares. And this has to do with my intuition, and it all comes in here. I've written it down. This is what I would think, I'm familiar with the biostat world, and these are commonly called generalized estimating equations, except that I've centered the treatment indicator here. I just centered it. And I'd say, well, if that's the case, I'm thinking that's what it is, weighted least squares, then you must be modeling the mean of y, given the treatment indicator, availability, and the controls by a linear model. But that's not what's going on. We're not doing that. We didn't even make this assumption at all. So what modeling assumption did we make? We made one modeling assumption. We made the assumption that the treatment effect, which is that repeated conditional expectation, has this form right here. That's the only thing what we did. What we gain by this centering is we're orthogonalizing this part of the design matrix. Think in terms of design matrices right now if you're a statistician. This part of the design matrix is orthogonalized with this part, so we separate that's how we get the robustness. We're going to assume, if I assume this, and I assume some moment conditions, like we have means and variances, then we get unbiased estimation. And we can do inference. We can do hypothesis testing. So here's the usual standard thing that you see statisticians state, that beta hat minus beta converges to square root n. N is the sample size, number of participants. It converges to a limiting distribution. And so now I can do inference. So what did I get here? I got some really nice, the fact that I randomized allows me to make this causal inference from this marginal treatment effect. That centering, the centering I used allowed me to separate the two parts of the design matrix, so I get robustness to my working model for the mean of y, just given availability, not averaging over treatment. So I can use any kind of I can use model checking methods to try and get a good model here. It's robust, though. If I mess it up, it's okay. I still get unbiased estimation. I will get better variance the better job I do. Lower variance the better job I do. I just want to contrast this to a lot of the literature, for example, on partially linear single index models, time varying coefficient models. These are models for high dimensional complex problems. You don't have this kind of robustness there. There is a price associated with this approach that we've developed, this weighted least squares. And the price is most clearly seen if you're a biostatistician and you use generalized estimating equations. So I'm going to just talk to you like you're a biostatistician for a second. So if I'm a biostatistician, I think, well, I have step count at each of 5 times a day over 42 days. I know they're highly correlated because they're on the same person, right? And if I can model the correlation between step count across time, I'll increase my signal-to-noise ratio. It's a natural thing to want to do, is to model the correlation structure in the step count over time. I mean, it's what I would want to do. However, if you do that here, you bias the causal inference. It's very interesting. And that bias comes from the fact that by modeling that correlation over time, I use future outcomes of my present treatment to determine the effect of my present treatment. So I adjust for future outcomes of the present treatment to determine the effect of my treatment, my present treatment, on my outcome right now. This problem has reoccurred in biostat about 4 or 5 times. We spent a lot of time going through the literature. The first time was in '84. Pepe and Anderson, I think, discovered that you have this sort of problem. In causal inference, you can never adjust for a distal outcome of your treatment when you're assessing the effect of your treatment on a near-time outcome. That's how you get bias. And that's what happens if you try and parameterize the correlation structure over time. Really interesting, and I'm going to speak to that at the very end of this talk, because I think as statisticians, this opens all kinds of the door for a lot of interesting methodological development. The choice of that numerator of the weight. Why this is the numerator of the importance weights I had there. So how would you choose that? Well, the purpose of the numerator is to help me have robustness when I misspecify my treatment effect model. So I'm going to give you an example here. Suppose I don't have any context, I just have an indicator, so I'm just estimating the average causal, the marginal causal effect, get a message versus not, averaged over everything. And so in my numerator, I use a constant probability. Okay, like 1/2. 1/2, 1/2. So P tilde is 1/2. Then you can, and then it doesn't matter whether or not it's a constant treatment effect over time, across context. That's okay. The treatment effect can be varying with time. Here I've written it here, where it varies with time. What you end up estimating is an average of treatment effects at each time, averaged over the fraction of time, weighted by the fraction of time you're available. So when I talk to my behavioral colleagues, I can say, well, even if my model is wrong, I'm giving you an average effect, average weighted by the fraction of time people are available. And that's something I can discuss with my colleagues. So the choice of the numerator of the weights is all about interpretability and help in the setting in which your modeling of the treatment effect is incorrect. So I want to show you an example of this with heart steps. Now in heart steps, we actually use this method to conduct our primary analyses. And so we're going to go through that. So heart steps, we had 37 participants, a 42-day study, 5 times a day. They could be provided a tailored activity suggestion. The phone randomized each individual at each of those times, probability 0.6 of getting a tailored activity suggestion versus probability 0.4. So here's our conceptual models. I'm always going to use these tildes because these are not really models, right? They're really conceptual models because we're only really modeling the treatment effect part. So we pre-specified our analyses here. Our first was we would just control for the pre-treatment step count. That's what ZT is. You can see it log transform step count in 30 minutes prior. And we have an indicator for treatment. Then the second analysis we wanted to run had to do with burden and habituation. We knew that this is a big issue here. And actually, I originally wanted, before we even started the study, I wanted to include a quadratic term in time. Because I thought at the beginning of the study, people will be confused, you won't see much of an effect. And then as time goes on, they'll start to respond to my messages. And then as time goes further on, they'll start ignoring me. and I won't get an effect, right? This is what I had in my head. But then before this, we were really struggling with this. We knew we wouldn't have a big sample. We only have 37. So we decided later to use just a linear trend to approximate any kind of quadratic by a linear. And so that's what you see here. So this DT, it indicates the day in study. So DT is 0 on the first day of the study, 1 on the second day, and 41 on the 42nd day of the study. So what that means is that beta 0 is the effect very early in the study, day 0, and then beta 1 is how that effect changes as the study progresses. Everything is log transformed with step count. If you're familiar with step counts, you'll know why. This is highly skewed data, and the log transform makes the data slightly more symmetric, and thus our large sample approximations will be more accurate. That's the whole purpose. That's the purpose of the log transformation, is to make our p-values, our confidence intervals more accurate. Okay, so we ran this, and I just want to talk to you about the results. So, so the first one, this is the primary analysis. We get an estimator 0.13. Now, of course, it's not intelligible because everything's on the log scale. So I'm just I transform that back, and this is approximately an increase of 33 steps. In these types of people, they get around 250 steps in a 30-minute time interval, about 250 steps. So this corresponds to about an increase around 33 steps if you get a message versus if you don't. You can see the confidence interval and the p-value. Then we included the trend with time. DT is 0 on the first day of the study, 1 second day of the study, and so on. So you see the initial effect of the treatment. We were, I think shocked would be a misstatement. We were so very surprised. Although we thought that we would have a larger effect that would decrease with time. So 0.51, it corresponds to 170 steps over an average of 250. So that's an enormous effect in this particular world. This is early on. Of course, this is negative. The behavioral scientist thinks it's habituation. So by about 3 weeks, it's a 42-day study, by about day 21, the effect is gone. The intervention's no more effect. And the thought is it's habituation. So I just want to indicate how this affected the planning for the next study. So in the next study, we're developing an algorithm to choose the probability for AT to bias the probability in the direction of whether or not it's working for that, the activity suggestion is working or not for that person. So we're going to run an algorithm. And we realized here that we have to be really careful, because if the algorithm tells us to always intervene, we're going to end up incurring a decreasing effect with time. So right now, we're planning to have a vacation from the activity suggestions. You'll have 2 weeks on, 1 week off, 2 weeks on, 1 week off. And this is specifically to deal with this habituation problem. Okay. So it turns out we actually, in these studies, this was a big factorial design. We randomized a great many things here. This was one of the other things we randomized, the kind of suggestion we randomized. And here we messed up enormously. And so I wanted to just show it to you to see how careful you have to be when you think about these problems. So we wanted to compare a walking activity suggestion. I gave you an example of that. It takes about, maybe it's a 5-minute request. Walk till you see a squirrel or something. And then there was the tailored sedentary reducing suggestion. Everybody loved these. I love this because this would I'd get a ping. It'd say, why don't you stand up and roll your arms? You feel great because you did something for your health. Not much, but you feel it. You know, you roll your arms, you feel good. So I love this. And there was some evidence in the literature, not from these kinds of trials, that actually once you get someone just to stand up, they tend to walk. So, okay, so we randomized between these two types. Always tailored. One is sedentary reducing. It only takes a half a minute or so for you to do. The other would be like a 5 minute. We kept the same outcome. Does anybody anticipate what's going to happen? How we messed up? Right now, already, we have messed up, big time. The last statement I just said, I messed up. We kept the same outcome. Why in the world should we expect this? Maybe we'll get a 30-minute step count, right? This maybe 5 minutes we might increase, but to think that we're going to have an increase in 30-minute step count, I don't even know what we were thinking. So this is really interesting because these are going to be factorial studies where the outcome for the different levels of the factors might be different. I don't know how to deal with that. So anyway, so here we run that. Now we have two indicators of treatment. As one might have suspected, this indicator here is active suggestion versus not. This is an indicator of anti-sedentary suggestion versus not. As one might expect, only the active suggestion. This was like, this was positive, but the p-value was like 0.7. There's just no evidence at all of, and I don't know if the anti-sedentary messages had an impact because we were looking at the wrong outcome probably. We did actually, because we were worried, no, this analysis was not pre-specified, so we were doing this after the fact. We were thinking about it. So the level of confidence you can place in that p-value is it's a lower level of confidence. We did interact this with time and study, and indeed, time and study, again, you see the deterioration of effects. So here's the results. The data indicates that there's a causal effect of the activity suggestion on the step count of the succeeding 30 minutes. This effect is primarily due to the walking activity suggestions. This effect deteriorates with time. The walking activity suggestion initially increased the step count of the succeeding 30 minutes by around 270 steps, just about doubling one's step count. But by 3 weeks in, it's pretty much deteriorated. So I want to go back to the next study. How does this help us about the next study? In the next study, we're going to randomize the anti-sedentary messages, but they're going to only be randomized at times that we detect that you're sedentary. And we have to use an algorithm that forecasts the number of sedentary times per out the day so that we spread our anti-sedentary messages throughout the day. We haven't settled on the outcome, but it will not be 30-minute step count. And then the vacation times that I spoke to you about earlier, we're going to use in the next study. This is my second to last slide, I think, I'm pretty sure. I just want to indicate something that if you had come to me, say, 6 years ago, you know, a study like this takes quite a few years because you have to write a grant, you have to get it funded, blah, blah, blah. So like, suppose you'd come to me about 6, 7 years ago and you'd ask me how to analyze this data. I would have said, well, you could use a generalized linear model. It's a natural thing. Random effects models. People in mobile health, behavioral scientists, use random effects models are the primary modes of analyses. A biostatistician might suggest a GE. Someone who's more on the machine learning side, slightly more machine learning might suggest more complex models that have more flexibility. The problem is none of these models were developed for a setting in which you're randomizing repeatedly over time. They were not developed for causal inference. They were developed, for example, many of these you can use them if you're looking at how stress and craving co-vary with time in an individual. These are natural models for that sort of thing. But that's not causal inference. You're not manipulating stress. You're not manipulating craving. And all of them seek to model aspects of the distribution which help you increase the signal to noise ratio, but they do it at the price of eliminating or biasing the causal inference. Very interesting. They just weren't developed for this problem. So in conclusion, causal inference is great here. I was able, because we had randomization, and I knew those randomization probabilities, I'm able to do causal inference based on extremely minimal structural assumptions. This is the joy of randomization. And a thing that arose here, and now I realize I didn't realize this until I worked on this problem. And this has to do with random effects models. It'd be interesting to hear some of your comments on this. So, like if you go back to originally, why did people, scientists, domain scientists, like random effects models? They usually like random effects models because they're trying to do person-specific predictions, person-specific effects. In agriculture, plot-specific effects, best linear unbiased predictors. That's the goal. That's the reason why they would use random effects, is they'd use empirical Bayes methodology to predict for that plot or that person what they might respond. That was the purpose. As a statistician, why do I use random effects? I don't use random effects for that purpose. I use random effects because they're modeling my correlation structure and my repeated measurements over time. And I know if I model that, I'll get a much better, I increase my signal to noise ratio. So I used random effects. I have one hammer, random effects models, for two problems. And it worked. It worked out great, right? I had my one hammer and I solved two problems. This is a setting where you have these time-varying treatment where my one hammer is not going to solve two very different problems. Very interesting. And I didn't even realize that we had one hammer that was trying to solve two different problems until I worked on this. And it would be great if someone figures out a way. We're going to need two hammers, one for each problem. Work like this, I just want to make it involves a big collaborative teams. I'm on a number of consortiums. There's computer scientists here, behavioral scientists, people who work on the human-computer interaction, so how the phone looks and presents the message to you. Statisticians, more behavioral scientists, all of us, app developers. All of us have to come together to conduct studies like this, to do this kind of work. And it's a joy. I learn a great deal from everyone. Thank you.
Great, so I'd like to take some questions. Susan, Jerry.
In studies where, as I understand it, for a given subject, you could be randomized to different treatments every, 5 times a day.
Right.
It strikes me that one difficulty with this kind of study is that people become disenchanted and compliance becomes an issue. We're already jerked around by our smartphones a good deal.
Right.
And I think I, in some ways, get annoyed if I really am invested and I believe in the project, but then the first 2 times I'm told to walk around for 30 minutes, and the next time I'm told to do nothing. Can you just comment on that?
Yeah, so that's the burden habituation problem. So that does make, this is why this is a reinforcement learning or a sequential decision-making problem, is because you have these incredibly strong negative delayed effects. The proximal effects tend to be primarily positive. Actually, we don't tell them to go for 30 minutes on a walk. We ask them for a 5-minute walk, but they may not do it right away. That's the reason why we have the 30-minute window. But so even the activity suggestions are not unduly burdensome, at least in this particular study. Okay. So what are we doing about this? So I too am like you. After I piloted a couple of these, I'm a great non-adherer. I produce a lot of missing data, as you can well imagine. I'm sure you would too, Jerry. I mean, we're expert missing data productions. Because, I couldn't tolerate these things. So I began to realize that not only do we need therapeutic actions we also need engagement actions. How can we give you so much back that you want to stay with the app? And this is important in a lot of ways. It's important for non-simplistic reasons. For example, if someone is struggling with, say they were alcoholic and they're in recovery right now, normally what happens is this tends to be more of a chronic disorder where symptoms wax and wane. And so we don't want them to disengage because we want to continue to kind of track them so that we can come back when they need us again. So disengagement, reducing disengagement is absolutely critical if we're going to use mobile health with chronic disorders. Medication adherence, diabetes. I mean, it is the most important thing. Forget about notifications to help you be more active. We have got to have ways to keep you engaged. Now, you may be engaged because you find the notifications useful. That's great. But right now, that's one way we could keep you engaged, is to really make sure our notifications are very highly tailored to the setting you're in and very actionable so that you feel like we're not doing stupid things. And we did a lot of focus groups, our team, and that seemed to work really well here because they were highly tailored. But you might want to keep people engaged by giving them other things that have nothing to do with activity, but are just engaging. They want to keep the phone on. You're giving them something they want in order for you to help them long term. So right now we have a study that's in the field right now. Mary and I talked about it, and it's all about engagement. There's no therapeutic notifications. There's only engagement notifications. So in this particular study, we're not doing anything for you. We just want something from you. We want you to answer some questions every day. So our engagement actions are all about giving you things that are unrelated to these questions so that you continue to give us the answers to these questions. And so long term, the way I see this going is we're going to have actions of different flavors. We'll have therapeutic actions and we'll have engagement actions. And we'll want to try and bring them together. You'll have to have vacations. You'll have to bring it all together so that people will stay engaged enough so that we can get their sensor data. They'll continue to wear the wearable. Yet we can provide support when it's possible. It's very interesting, the iatrogenic effects in this setting. This is what makes it interesting as a someone who's interested in data.
Sure. Sorry, Richard.
Very nice talk, and the thing that strikes me is because when I'm talking to people about designing trials, is when there's adjustments for a number of other factors, the sample size calculation is tricky, and this is kind of a problem that seems hard to imagine how you would figure out how many subjects you need to pick up a specific effect.
We have an app, a web applet that behavioral scientists now are already going to, and you feel it. So what they have to do, let me just, I have to make sure I'm right. They have to give us several things. They give us what they think the average effect, marginal across time. They standardized effect. They give us, it's a web thing, so they see little graphs of how that effect may change with time. They pick one of those graphs. They see graphs of how availability may change with time. They pick one of those graphs. I can't remember if there's anything else. And then it spits out a sample size. And there's R code. Yeah, it's totally cool, and it works. It's working out great. I mean, so far, of course, part of it is we're in the instruction, this web app, it's continually reminding you to be very conservative. Don't assume people are, like, for example, if you think people are going to be available 90% of the time, but they're only available 50% of the time, you're going to mess. So there's a lot of guidance there to try and choose conservative options as you go through the sample size calculator so that you get a reasonable sample size. But because we are using repeated observations over time, you do get smaller sample sizes than one normally does. Now, I just want to be clear with everyone, we are using like robust standard errors throughout. I mean, we're not making assumptions on the correlation across time. I mean, that's absolutely critical here. If you see step count data, it is so highly chaotic. We really don't want to make a lot of assumptions.
I wondered if you could also think about adaptive sample size estimation, like when you start to collect data, if you're surprised about the variability in a given set of individuals, you might revise.
Yeah, we haven't really, because I'm in the NIH, classical NIH world, so I tend to always go for things, so there's the gold standard, and then there's something that's much better than what we're doing now. And I tend to move on that path. And so right now, like when we write the NIH grant, I want, this trial design is so, out there that so the way we do it is everything else sort of looks comforting. The primary hypothesis looks comforting. The sample size calculation looks comforting. Nothing, so you have novelty, but you have a lot of comfort. And we've been very successful. I mean, we have quite a few of these trials, and they're being now run by other researchers that aren't even involved with us. Yeah. So I think doing it in that way is useful, even though it doesn't get me. I'm not going to the gold standard. Yeah.
Any final questions? So then we'll move to M3 for the reception, but maybe before that, let's thank Susan for the presentation.
Thank you.